Good morning. In the previous lecture, we see there is formation of 3s energy levels and 3s energy bands. In a similar way, it might be possible to combine 1s, 2s and 2p orbitals to form 1s, 2s and 2p energy bands respectively in a crystal of sodium metal. The formation of energy band in a crystal takes place only when there are large number of atoms. Second, the atoms are sufficiently close to each other. Third, the combining atomic orbitals possesses matching symmetry. Fourth, the atomic orbitals are of the same energy and have sufficient overlap. Fifth, the interaction between the atomic orbitals is strong. Sixth, the energy band covers all atoms and belongs to the whole crystals, that is, complete delocalization of electrons takes place. See, in this figure, there is formation of bonding molecular orbitals and antibonding energy orbitals, that is BMO and ABMO. Sodium exists in the vapor state as a free atom. There is no energy bands. The electrons occupy atomic orbitals with separate and distinct energy levels. As the sodium atom are brought closer and closer, the interaction between various atomic orbitals increases so that the width of the resulting band also increases. See, in this figure, we see 1s, 2s, 2p, 3s and 3p bands are get overlap, and there is overlapping of energy bands, and it will be shows that there is the broadening or increase in the overlap overlapping of atomic orbitals and energy bands also. The potential energy diagram, of which the energy state will now appear, we see in the figure. The equilibrium position indicated by the dotted lines in the figure. This increase in the width of the energy band with decrease in the interatomic distance is shown for 2s, 2p, 3s and 3p levels in the sodium crystals. It should be noted that the lower energy orbitals 2s and 2p interactive to form energy bands at smaller intersect or make distance, while the higher energy orbitals 3s and 3p interact to form the energy bands at the greater distance. The equilibrium position is indicated by the dotted lines in the figure. This is 3.71 angstrom for sodium crystals at which 3s and 3p energy bands overlap with each other, that is broadening and as well as the overlapping of energy bands occurs. The situation can be also summarized diagrammatically as in the figure. The energy bands are absent for the free sodium atom in the vapor state, and the energy levels are diagrammatically indicated by a line. This takes place because the sodium atoms are not close. Thus, the electron occupy atomic orbitals with separate and distinct energy levels. The energy bands are formed when the sodium atoms are brought closer and closer as shown in the figure. Therefore, an energy level which is diagrammatically indicated by a line in an isolated atom has to be represented as a band in a metallic crystal. Figure shows the overlap of 3s and 3p bands with atomic orbitals reach the equilibrium position in the crystal. Now we are going to see the formation of these energy bands, and they are occupied by the electrons. Thus, the filling of electrons in the 3s bands of sodium metal. In general, when there is an overlap of n atoms in a solid structure, n molecular orbitals will be obtained. Each molecular orbital in a band can accommodate 2 electrons as shown in figure. See the filled bands and empty bands. As there are the n number of atoms that is combined, they provides the n number of atomic orbitals, and thus there is formation of n by 2 BMO and n by 2 ABMO. BMO get filled by the electrons, and thus there is the filled orbitals. That orbitals forms the band. That band is the filled band, and the empty orbitals, they forms the empty band. Thus, due to the filling of electrons, thus there is formation of the bands, filled band and the empty bands. In case of sodium metal, there are valence electrons of sodium atoms. Hence, there are n energy levels. The maximum number of electrons that can be filled in each molecular orbital are 2. Thus, n electrons of n atomic orbitals will be filled in n by 2 number of bonding molecular orbitals. Therefore, 3s band in the sodium metal is half filled. Electronic energy bands, how they will be formed, and we are going to see that electronic energy bands. According to molecular orbital theory, the formation of many molecular energy levels takes place in the metal having n atoms. These closely spaced molecular orbital energy levels from the energy bands for each type of orbital. We shall now consider the filling of these energy levels by the electrons. There are some important points are explained in this regard with the distribution of electrons. The inner electron of the metal are filled in closed orbitals and not in the bands. The valence electrons are filled in the delocalized energy bands. Second, the valence orbitals and the higher energy empty orbitals merge into the energy bands. These bands are delocalized, that is extended throughout the crystal structure of the metal. Third, as for the free atom, the distribution of electron takes place in the molecular orbitals or the energy level bands. Fourth, Ne curves. These Ne curves gives the way in which the electrons are distributed in the energy band within the various possible energy levels or states. The complete distribution of electrons between the range of energy levels in an energy band is given by a curve called as Ne curve, where N represents the number of electrons in each energy band and E stands for the energy of the band. The Ne by dE gives the number of electrons per unit volume of the material with energies between E and E plus dE. The energy distribution of the electrons in a band is given by plotting Ne curves, that is Ne versus E. The energy curve can be represented as in the figure. See here in the figure there is Ne and E. They are represented energy band. The shaded portion shows the half-filled band. Here the energy is plotted horizontally and the vertical region under the curve indicates the number of electrons that can be accommodated at each volume of the energy. Shaded area in the curve represents the filled band